All right, can folks on YouTube hear us okay? Let me double check. I think so, yeah. Okay, I think, yeah, we already have, I think we already have a good amount of people, so we can probably get started. All right, welcome everyone to another episode of GPU Mode. Like, this lecture today is like a very special one for me. I've been wanting to have Chris come give us a talk for like at least a year now, like basically from the origins of the server. So I'm glad he could finally make it. So today is really going to be like a very deep technical talk about a lot of stuff, like ranging from GPU programming languages, programming models, metaprogramming, compilers. And so I'm really thrilled that, like, so first off, I'm co-hosting this with like my good friend and colleague, like Alban de Maison, who's one of the core maintainers for PyTorch. And the two speakers are going to be Chris, legendary Chris, and Abdul, who is basically one of the core maintainers of all of the Mojo's GPU support. So yeah, if you have any questions, I think both Chris and Abdul told me that they'd love to take them. If you have any hot take questions, also feel free to ask them. And yeah, without further ado, Chris, please take it from here.
Amazing. Well, thank you, Mark. I'm really time for us and really excited to talk about what we've been building for a really long time, and I hope you like it. As Mark warned me, nerdery is acceptable in this audience, and so if you want, I'm happy to nerd out about things as well. But we'll dive in. So what are we going to talk about today? We have a whole bunch of stuff. So we want to talk about a short version of like what is GPU software looking like today, and therefore what do we want to do about it. We're going to introduce Mojo, talk about powerful metaprogramming and why it matters, talk about portability, talk about tile-based programming, talk about composing operations, talk about performance, because accelerators are all about performance, talk about tools, talk about comparisons to other things, and then hopefully inspire you to do something really cool. So this is a lot. This is not a 10-minute talk, but hopefully it's interesting to some of you. So let me give you a warning. So there's a lot of things happening in AI. There's a lot of systems out there. There's a lot of claims. There's a lot of BS. So today, the reason that we have not given this talk until today, and I love Mark and I really want to do this, is that this talk is not vaporware. So everything we're talking about today is stuff that you can download and use today. You can use it for free at any scale. You can use it on CPUs and multiple GPUs, including AMD and NVIDIA. This is not a vision talk. This is real. So I know that's a confusing thing in our industry sometimes, but this is a really big deal. And we want to make sure that we're extremely grounded on things that you can have a clear call to action to do. You can learn, you can dive in, you can tell us where we did it wrong. And so like you can really dive in. And that's really, really, really important. So one of the reasons that this is a why now is that we just open sourced possibly the biggest open source GPU kernel library ever. And so this is almost 500,000 lines of Mojo code. And so if you go to GitHub on modular/modular, you can find it today. This is under an Apache 2 license. Please check it out. We'll be pulling highlights from the code, but this is a really big point for us. And so we're really excited about this. So let's take a quick dive into GPU software today. So if you're interested in GPU software, then I would love for you to read my blogs. I'm writing a whole blog post series about OpenCL and CUDA and like the history and things that have worked, TVM and XLA and Triton and like a whole bunch of different systems, because there's so much both modern technology that is important and powerful for what is running the world, but there's also a lot of history. And there's a lot of things that many of us wanted to work, but didn't quite work out the way we thought it would. And so this blog post series dives in, and it's up to 9 parts now. Hopefully part 10 will be out next week. So I'm not going to talk about that. I'm just going to give you the super, super highest level take on this, because we want to talk about our stuff today. So first of all, what is the problem? Well, the problem is that there are too many languages, too many systems out there. And so today, modern AI has got a many language problem. We want to be using Python. It gives us quick iteration. It's easy to use. This is where the whole world and AI is converged. But then when we want performance, we end up having to drop down and rewrite things in C++ or Rust or languages like this to get performance. But then, of course, AI is about GPUs. And so then you face this reality that now you have to rewrite again to get into CUDA. CUDA is a different world. If you want to get to other hardware, you have to rewrite it again. And so what AI today looks like, particularly if you care about performance and state-of-the-art research, is that you're constantly rewriting code. Now, rewriting is a pain. It's expensive. It has lots of different problems that are well known across software. But the actual big problem here is that every time you rewrite, you've split your team. Because if you're doing modeling, you're in Python. If you're in GPU kernels, you're doing CUDA. But now you have a split brain problem where if you're straddling this boundary, you're having to keep multiple different paradigms in your brain. It's just not a good use of our time. And so this is one of the big issues that the hardware enablement industry is facing, but also AI and a lot of other things. Well, because of this, we now have complexity. And I'm not trying to pick on any individual system, but roughly every system ends up looking like this, where it's many different things cobbled together, lots of different hardware that gets integrated, many open source projects get like extended and get different features over time. And so the consequence of this is if you're an AI engineer building on top of this stuff, well, the problem is that you pick it up, you want to deploy in some use case with some quantization thing on some piece of hardware, and it just doesn't work right, or the performance is bad, or you get some weird stack trace. And the problem is that every layer of the stack is evolving and wasn't designed together, and it's often 15, 20 years old, depending on the technology you're using. And this is a huge problem. This is slowing us down. So when I look at the systems out there, and here's a really short and very simplified view of the world, zooming into kernel programming and GPU programming, because that's what we're here for, there's three things that really matter. One is performance. If you're using a GPU, we know they're expensive. We want to get all the flops. The second is usability. We have so much to get done. We want to be productive. We want more people to get into GPU programming, and usability is key to that. And third, portability. We want to be able to move to different hardware. We want to be able to look at new opportunities, different specialized use cases, and we want to be able to move our code and our algorithms over time. And so if you look at the existing systems that people are writing kernels in, they break down into different spaces depending on the trade-offs that they're looking for. And so notably CUDA, I mean, CUDA is amazing. It powers pretty much everything, a huge swath of AI, not everything, but a huge swath of AI. CUDA started out by being the king of performance. Recently, they've added a lot of usability features with Cutlass and some of the Python things they announced at GTC. And so maybe it's getting better for usability. But of course, CUDA is not at all about portability to other hardware. If you get Triton, for example, Triton's a super well-known, super widely used DSL. I love Triton. It's tons of respect for it. It really does two things for us as GPU programmers. One is it really improves usability. And so that's a huge productivity benefit. A lot of people love it, particularly when you're prototyping. It's pretty good at portability. And so you can get portability of some kernels across like AMD and NVIDIA, for example. But with Triton, you give up a lot of performance. And so that's okay if your use case doesn't require performance, but because the contribution in this usability and portability space is really key. There are other technologies, OpenCL, for example. OpenCL, again, a much older technology, doesn't really do tensor cores well, so you don't get performance, but it's portable to like FPGAs and things like this. It's also not super usable and kind of has fallen behind in various ways. There's also many other things. ROCm is amazing for performance on AMD, but it's not focused on other usability or portability features. And so if you look at these systems, right, the challenge is we want all three. And there isn't really a solution out there that is able to provide that today. So I'm a compiler person. That's what I'm known for. And so I spent years trying to say, let's go solve this by building the sufficiently smart compiler. And I worked on XLA, and I've worked on lots of other different things in the MLIR world. And for a lot of time, but an entire industry has been trying to prove to us that AI compilers can be the solution to the problem, right? And we point out that kernels have all these problems, and we want to be able to have generality, and compilers are good at generality. But there's a huge problem with AI compilers. Gen AI moves really fast. The algorithms and the research, everything's moving all the time. And unfortunately, there are not enough compiler engineers in the world. And also, compiler engineers are often not experts in algorithms, in the microarchitecture, the evolving use case. Compiler engineers don't know all of the different things going on, particularly because there's so few of them. And this becomes a bottleneck. Of course, we also don't want to have other people like kernel engineers have to become compiler engineers to get things done. We also have AI engineers and other people higher level in the stack. And so what I love about AI as an ecosystem and as a community is that success is really about getting all the different personas to be able to work together. And so AI compilers as a direction really kind of lost that beat and tried to put everything in the compiler, which made it so as a kernel engineer, you have to end up reading IR or something, right? Which was really quite unfortunate. So what I want to have happen is I want to have this unified Gen AI native software platform. And this is a big, bold quest. Like, this is an industry scale problem. I'm not the only one that wants this. And so what I think we need to do is go back and rebuild this thing from first principles, take all the lessons learned from all these systems and do something quite new. So what do we want? Of course, multiple different GPUs from different vendors. We want full performance of the silicon because GPUs are all about performance. We want usability, fundamentally. So this, of course, is what Modular is about. So I'm happy to finally be able to tell the world about what we've been doing, because we've been at this for quite some time, and it's very, very, very exciting. Like I said today, this is not theoretical. This is all real. So what are we doing? So at a high level, and we'll get into code for sure, trust me. But at a high level, we're saying, let's build an entirely new programming language. Let's build an entirely new AI framework. Let's build an entirely new AI stack, all the way up to serving and fancy cluster management and all this entire AI vertical from first principles for heterogeneous compute, for Gen AI, for the today use cases. This is not about do the thing that made sense 15 years ago and try to duct tape it. This is really rethink and challenge these assumptions in a new way. And so we started by building this and testing and validating on CPUs. CPUs have a lot more diversity than even GPUs, because there's all the microarchitectures, a lot of weirdness, different macro architectures like ARM64 and things like this. And so we brought that up. We then brought up NVIDIA. And so we have full support for NVIDIA, including all the data center and also the consumer GPUs. And so 4090 and the Blackwell and like all this kind of stuff, fully supported by Max today. We also support AMD. And so AMD MI300, 325, download Max, download Mojo. You can today use all of these devices and it just works. And in fact, the same image works. And in fact, we're not using things like CUDA to run on any of these devices. And so when I say this is a first principles rethink, this is a really big bet. This is a really big swing at a very big set of industry problems. And so this is why I'm so excited to tell you about it. And we're excited today that we can not just tell you about it, but show it to you and you can try it yourself. Now, in the future, there's a lot of hardware out there. I'm a hardware nerd, among many other things, and so we'd like to be able to catalyze the future. But today we're talking about what's available today. We're not talking about any future potential or any exciting new directions. So let's dive in and talk about Mojo. Mojo is, we think, the best way to program GPUs. We've been working on this for years now. It's really hard to do what we're doing, but we'll talk about why we decided to do that, what it means, and then we'll give you tons of examples on this. Now, while this talk is focused on GPUs, because hey, we're here at GPU mode, there's a whole Python thing going on too. And so if you have a lot of Python code and you want to go fast, okay, well, there's a whole different line of work that's super interesting for that as well. So let's dive into this new language thing. So wait a second, building a new language. And by new language, I don't mean a DSL. I don't mean take something that exists and change it. I mean an entirely new programming language from scratch. Well, this is a terrible idea. Let me tell you, like everybody will tell me, but it's common sense that building a new programming language is a bad idea. And there's lots of good reasons for this. It's that they don't get adopted. If you have to retrain your team to learn a new language, that's a huge expense. It's also extremely difficult to build them. You have to get people to use it. This is why many people in AI just use Python and hack it with the DSL instead of building an actual new language. And so being successful with a language requires you have a consistent vision. This takes years of time to do. You need to be able to pay for it. You need to be able to attract the kinds of people that can actually build a language. And it turns out that there's a special kind of nerd that actually wants to do this kind of work. And they're brilliant, but there's very few of those. You also have to be able to build something that people care about. And so if you're going to build a language, there's a million hobby projects out there. What I care about is doing something that has impact and actually gets adopted. So end to end, this is just an expensive proposition. And so there's a very specific time and place where it can make sense to do this. And fortunately, we think heterogeneous compute is that time and place. And so why do we think that is? Well, building new languages is the only way to get the best thing, right? We want something that is really powerful. We want to make something that has high impact. We want to make something that an AI developer, kernel engineer can fall in love with. We're not trying to do a point solution, a quick demo, something that's research quality. We want something that's actually good and that can lift the industry in a way that very few other systems have even tried to do. And so when you look at these things, we think we can check all the boxes. Like, we think we have a clear vision of what we're trying to do. We've certainly been working on this for years. We've certainly paid a heck of a lot of money to get some very, very smart people together and actually build this and continue to evolve it. And I'll just say, from a personal perspective, like, I've done this before. So I built OpenCL at Apple, and then gave it to Kronos and scaled, and it went on to scale it. I built an entirely new C++ parser and ecosystem for Objective-C and C and all this stuff called Clang. Super hard to build a C++ compiler, by the way. I've built an entirely new programming language, Swift, and launched that to the world. It was a very great nights and weekends project that scaled. But what I've learned across all these journeys is you need all of these checks. Like, you need an amazing team of people. No one person can do all of this alone. You need to be able to see it through. You need to be able to execute, and you need a good vision. And so this is what we think has been really quite special about Modular, is we've provided that opportunity to bring together the people and the talent and into this opportunity. And we're very, very, very excited to talk about it today. So what is Mojo? Well, so at a glance, it's a Pythonic systems programming language. So let me break that down. So Pythonic, it feels like a member of the Python family. And so we're not inventing new syntax. We decided that we like Python, the world likes Python. Let's use what's great about Python, which is its syntax and its ecosystem. The second part of that is systems programming. So forget everything you know about Python. This is fast. So this is not using the Python implementation. This is using the Python language, which is a very different thing. Now, as a language, it's not just you need to be able to have syntax. You also need a full toolchain. You need editor support. You need a whole bunch of other things. You need platform capabilities, a debugger. So building a language is really, really quite hard. But this is what Mojo entails. Now, like I said before, you can download this for free. You can use it for whatever you want. We're open sourcing all this stuff, and we have quite a large community of people that are already excitedly using it for different things, which is super cool. So, but what is Mojo really? What we're doing is we're saying, take the developers in the Python ecosystem and give them new superpowers and new tools, but then take an entirely new generation of programming language and compiler design and bring it together into a novel combination. And so today, I'm going to resist myself and not nerd out too much about compilers. Happy to do that some other place. But we're going to talk about metaprogramming and some of the programming language things, and then we're going to show you what that means for you as a GPU programmer and why maybe someday you can be saved from C++. But going into this, even though the code looks very familiar and it's super easy to learn, and it looks like Python, please, this really is not a Python DSL. This is a completely new programming language that happens to use the best syntax in town. Okay, so what is Python? What is Mojo? Well, I said it's fast. What do I mean by that? Well, you can do pretty much anything in Mojo. It's a fully general systems programming language. And so you can go write tokenizers. Here's a BPE tokenizer, for example. When you measure it against something like Python, this is a thing that I always get asked about, is we're not trying to make a faster Python. So yes, it is 1,000 times or 10,000 times faster than Python. But what we're actually doing is we're working back from speed of light of the silicon. And so this example is a CPU example, but we'll talk about GPUs shortly. You can't give up any performance on GPUs if you want the best TCO and performance. You just can't. And so on a CPU, this means you get full power of SIMD, threads, NUMA. There's a whole fancy compiler that I'm resisting talking about, has correct tail calls, all these things that you'd expect from modern language. If you're curious, we have a whole blog post that talks about comparing Mojo to Rust. And Mojo is a much more modern language that is learned from Rust and Swift and many other things. And so, yes, in cases, it's actually faster than Rust, which hugely polarizing. Some people don't seem to understand that Rust is not the be-all and end-all of performance. But CPUs are not all. It's also about GPUs. And so one of the cool things, and we'll talk about this extensively today, is that you get the full power of the silicon. And so you get a very familiar GPU programming model. So yes, you can go all the way down to threadindex.x and blockindex.y and do this kind of stuff. One of the really cool and very important things to think about Mojo compared to some other DSLs is that it's completely general. And so I'm going to talk a lot about AI because that motivates me a lot, but you can write ray tracers, you can write any kind of GPU program you want. Go tackle biochemistry and go to HPC simulations. Everything we talk about today is quite general, and we've focused on AI, but that doesn't mean that you have to. You can use all this technology to do pretty much anything that you can do with an accelerator. So now, one of the things that I love about GPUs is they're weird, right? And so this is something where there's so much innovation in D-types. Hopper added TMAs. They change every generation. Blackwell has crazy new features. AMD has its own take on things. There's a lot of hardware out there. And so what we'll talk about multiple times over is that you get the full power of the hardware. And so we'll talk about how this works. But this is not a watered down solution. This is not a make it easy for the simple case. This is a give experts superpowers, make it easy for them, and then enable the super experts to build powerful libraries that people that are learning can build and scale into over time. And so, yes, you can go all the way down and program the TMA. You can utilize the low-level Tensor Core stuff if you want to. Hopefully, you'll use the higher-level abstractions we'll talk about later for tile-based programming, but we don't want you to be, there's no like headroom that you run into that prevents you from getting the hardware.
So
now, if you are a compiler,
so Chris, I'll interrupt you.
Yeah,
I think this might be a good time for questions.
Yeah,
I'm gonna add like all the mods back. I read your series basically on like sort of like the history of CUDA and sort of like the design trade-offs like you had with Mojo, and kind of one of the things that you said that like a major limitation for Triton is that like once a new GPU generation comes out, there's all these new things that need to get supported, and this is like a manual effort. Like, isn't that like inevitable? Like basically any programming language needs to deal with this because you can't anticipate what new hardware intrinsics will be made available.
Nope. Give us a few slides. We'll show you how to go directly to PTX. You can go directly to low-level assembly. Like, this is not the talk where we're avoiding PTX. Like, we'll go all the way down to the silicon. So, and I'll show you how that's done, and I'll show you how you do that without even changing the compiler. And so this is the challenge, right? So those DSLs out there, the problem is that enabling a new piece of silicon requires changing the compiler. You do not do that here. That is not necessary, and I'll show you how. So that is a fundamentally different thing, and this is one of the reasons why, like, this is a new category of technology. So,
all right, let me get out.
Sorry, I didn't mean to scare you away, Mark. So no, I'm sorry if I'm like being too excited. I'm pretty excited about this, and a lot of things that I take for granted because we've been working on this for years is really non-obvious, but yeah, you get full power of the silicon. We've implemented new GPUs and things like this without changing the compiler, which is really quite important. And also, I'll talk about the way you do that is all open source. So we'll show you some of that code. So okay, so I'm just trying to frame the high-level bits before we dive in. Another thing with Mojo being a fully designed from first principles for modern compute is that there's a whole thing that I'm not going to talk about much at all today called a graph compiler. And so in AI, you have a lot of things like you have a CILU activation function. Well, you don't want to write all the permutations of here's your matmul and here's your CILU fused into it. And so autofusion, memory planning, static specialization based on known dimensions, all of this stuff composes, and it's not the focus of today because we want to talk about GPU programming, but the best kernel is the one you don't have to write. And so when we talk about usability, it's a big deal that you don't have to write the cross product of all the things. And so this is something that Abdul will touch on, I think, later, but we'll get back to this. What about tools? Well, building a language is a real pain in the butt because you have to build support for the LSP in your editor. You have to build a debugger. You have to build so much infrastructure, so much technology. But the benefit of that is you can have amazing tools. And so Mojo directly integrates with CUDA GDB, Insight Profiler just works. Like all of these things you'd get with CUDA come over directly and they just work. This is huge. And so if you care about performance, it's very difficult in our experience to get performance without having a profiler and not being able to understand how your code maps to what you see in the profiler. And so this is a really big deal. So I want to get to concrete code right now, and I'm going to talk about the major content of the talk is talking about like strict walkthroughs of code that we've written and how you program GPUs and do all this kind of stuff. But there's one language feature that's essential to understand anything in this talk, and that's metaprogramming. And so Mark, this gets back to your question of like, how can I enable new hardware without changing the compiler? The answer is metaprogramming. And so whereas those AI compiler people, including myself in past lives, wanted to take power away from the kernel engineer and put it into the compiler, metaprogramming in Mojo is how we flip that narrative. Our goal is to give superpowers to kernel engineers so that you have the power that was traditionally locked up in the compiler, instead of having to go call a compiler engineer just because you want an incremental feature or a new D type. So why do we want this? Well, we need hardware generality, like we're talking about, portability, capability, new weird features, that deep seek instruction of the day. We want single source of truth. A lot of algorithms are actually quite portable at the right abstraction level, and so we want to keep the stuff that's common. We want things to be parameterized. Different GPUs have different warp lengths. You want a different unroll factor, tile factor, things like this. And so you need to have configurable algorithms, right? The state-of-the-art way to do this today, sadly, is C++ templates. Okay, and so C++ templates are a pretty well-known thing. I'll just speak for myself. I don't love C++. I've written way too much C++ to love it, and it's because template error messages are a nightmare. It's really slow to compile. I can never figure out how to use string as a template parameter. Just simple things don't work, and so this is just a freaking nightmare. But the requirements, the benefits of doing this are profound, because you can lift code from runtime into static compile time, and you can get these reconfigurable algorithms. So with Mojo, again, it's a Python family language. What we realized early on is that Mojo needs what Python already has. And Python, at least for CPUs, has really powerful metaprogramming features. It has things like decorators and metaclasses and reflections. It has dunder methods. It has all these things that make it powerful and easy to build very amazing libraries that enable things like PyTorch and stuff like this. But of course, Python isn't known for its performance, and there's no way this is going to run on an accelerator, right? And so when we look at this, we say, okay, let's be inspired by this concept, but let's do it in a very different way. This is basically our relationship with Python, by the way. And so let's do all of this fancy stuff, but instead of doing it at runtime, let's do it at compile time. So how does this work? So Mojo has this thing called a parameter. So parameter is like comp time. This concept comes and is inspired from a language called Zig, and there's other languages that do this as well. This isn't some novel concept, but parameters, you can think of them as being kind of like templates, template arguments. And so here's a struct in Mojo. This is SIMD. This comes straight from the standard library, by the way. And it has two parameters. One is the D type. So is this float 32, or is this float 8, or is this int 64, or is this what is the data type? And then what's the width? And so because these things are in square brackets, these things are bound at compile time, and then this code is instantiated just kind of the way you might think of it as a C++ template. Well, so how do you use this? Well, functions can also take parameters. And so this function, first class SIMD, takes a width, and it says, hey, I'm taking x, which is a SIMD, and it's a float 32, and it has some parameterized width, right? And so now I can build generic algorithms that work over any width of SIMD, and in this case, it wants the thing to be float 32. Mojo has another thing called an alias. Again, you don't have to memorize all this. I'm just kind of painting the landscape here. What an alias is an alias is a comp time variable. And so float 32, this isn't built into the compiler, by the way, because we don't build hardware things like, math into the library or into the compiler. All of math, all the primitives, all the integers and floats and SIMDs and stuff like this are defined in Mojo code. You can read the code. And so float 32 is just, you can think of it as like a typedef. But alias is a much more powerful thing than a typedef, because it can be an arbitrary expression that is computed at compile time. So again, this is probably not making a ton of sense to you. We'll see a lot more examples later, but just think of these as way better than C++ templates, and you're kind of in the right ballpark. Now, the reason this is better than templates, there's a bunch of them, but one is that in C++ you have normal code, you have for loops and if statements and stuff like this, and then you have templates and you have partial specialization, and so you have two different worlds that are very different to program. And what Mojo does is it pulls together the actual language and the meta language. And so what this means is that you can use a for loop at compile time, you can use a for loop at runtime, same thing. This also means that pretty much anything you do at runtime can also be done at compile time. Basically, the only thing you can't do is I/O. And the way this works is that if you do something at compile time, it can be arbitrary code. You can call malloc. We'll look at an example of that. The interpreter actually goes and symbolically executes that, and then it gets the result. The result might be an integer or floating point value, or even an array in memory or something like that. It just puts the output in your binary. And so you can shift an arbitrary amount of computation, for example, all that really complicated tensor indexing math, out of runtime into compile time. So, okay, if you're a concrete person like me, sometimes it's helpful to look at an example. So here's a really simple example of some Mojo code. This is just filling a list. A list is like an STD vector. You can think of that as in C++, if you're familiar with C++. And so all this is doing is saying, like, create values. It's a list of integers. Loop over from lower bound to upper bound and append an integer to it and return the list. Okay. This is not super complicated code. I'm trying to pick something simple before we blow your mind later. So the thing to keep in mind is this list is malloc, right? So this is like a resizable vector type thing, right? And so this is a very dynamic function, and you can call this and you can get a list from 17 to 97, and it does what you'd expect. Now, this is a function, but functions can be called at either compile time or runtime. And so I'm not going to show you runtime. You know how you can just call a function in Python, it's fine. Well, this thing alias that I showed you before, I showed you it was kind of like a type def. Alias says, compute this value arbitrarily at compile time. And so here's an example of a function that says, give me vec. Vec is the result of calling fill of 5 to 20. And so at compile time, this goes off and creates a list, which is empty, and then it goes and does a for loop and goes through the elements in that range. It does append, which, by the way, does a resizing, reallocating thing that it would do, and it returns back a malloc pointer with the capacity and range and stuff like this. And so what the compiler does is it puts vec down into memory, and then it's all been computed. There's no for loop that happens at runtime. You just loop over the pre-allocated set of memory. Boom, you've just got the result. And so this is just a very simple example of shifting, a fairly arbitrary chunk of runtime logic into compile time. Now, this seems weird. This is a goofy example. So here you go. This is meant to be simple, and hopefully you kind of grok what's going on here. This becomes extremely powerful when you get into much more real GPU programming examples that we'll show you. Now, metaprogramming is not just about storage. It's also about building powerful algorithms. And so this is something else that will come up. And so if you go look at the SIMD type, again, like virtually all the code in this talk, this is public on GitHub. We'll share the slides later, and you can go click on this link or find us in the Modular repository. SIMD has algorithms, right? So one of them is a horizontal reduction, so reduce max. And so what we can do is we can use this compile time if statement, parameter if, that says, hey, use, I guess I forgot to update the slide. This should say size. Use, if the size is 1, just return the element. And so a reduction of one element is just the element. But otherwise, we have to go do different special cases. Well, so, hey, guess what? There's all these special cases for different architectures. Well, now we were talking about before, okay, well, I want to be able to do maybe a recursive decomposition. And so here we do a recursive decomposition saying, hey, if the size is 1, then use it. If the size is 2, then get the max of the 2 elements. Otherwise, cut the vector in half and do a slice of each half of the thing and do a max of each half, and I get a nice vector reduction loop, or it's not a loop, I get inline vector reduction in a very simple way on x86. But maybe if I'm floating point, I want to do something else. If I did this and do this other thing, hey, LLVM has some intrinsics. I can plug all that directly into Mojo, and I can write this in my code. I can write what is effectively a little compiler for an arbitrary horizontal reduction operation the way I want to as a Mojo programmer. And so this is what I mean when I say we're taking these algorithms out of a compiler and putting them into libraries, because what you would do otherwise, for example, MLR has this like vector dialect and has piles and piles and piles of special case logic for different architectures, different things, and it's very opaque and it's not really optimized. It's hard to understand what it is. You have to be an MLR compiler expert to do this stuff. Now you can just write some if statements. And that's really, really, really different. And particularly in AI and for kernels, you get really high abstraction things you want to express. And writing piles of C++ code in MLR get just in your way. It prevents velocity. It's very difficult to work with. Now, this is also really cool, and I'm just going to touch off this because not just are things parameterized on values like an integer or a string or something like this, but you can use arbitrary types. And so you can use, for example, higher order functions as compile time metaprogramming combinators. And so here's a vectorized algorithm, and this will probably go over most people's heads on first glance, but maybe if you rewatch the video 10 times later, we're saying this vectorized algorithm is parameterized on a SIMD width. So this is a compile time value for what is the width I want to vectorize. Like, do I want eight elements? And then I say, I'm taking a function, and this function takes an arbitrary compile time function. So maybe I want to take sine or cosine or powf or whatever. That function is parameterized on a width. And now this function can be passed in, and I have an actual dynamic size. And so if I want to go vectorize some algorithm across n elements, well, how do I do that? Well, I want to be able to say, okay, well, on my architecture, I want a SIMD width of 4 or 8 or something like this. And so for first blocks of 4 or 8 elements, pull off 8 elements, shove them into this function with the full SIMD width, and boom, do a block of operations at a time, whatever my SIMD algorithm width is. And then I have a cleanup loop. And so for the cleanup loop, use the same function, but use a vector length of 1. And what I get is I can now compose something like sine or cosine or element-wise multiplier or anything like this. And now I can have a generic vectorized algorithm that just works across arbitrary things. Now, there are smart compilers out there, and this is me. I think this is the last time, probably not the last time that I'm complaining about compilers. There's OpenMP, there's all these things out there, but the problem for you as a kernel engineer is if you're using things like this, you'll get these pragmas and other features where you say, please vectorize my loop for me, and it fails. So in this case, I'm not doing anything that hard. I'm saying go over some pointers, and maybe I got restrict wrong or something, I don't know. But I didn't get vectorized code. Well, by doing simple composition of libraries, this vectorized algorithm guarantees that the code will be vectorized on the SIMD width that you asked it for. And so this is a completely different thing. And if you don't like my vectorize, you can write your own. That's quite different than what people are used to. And that's one of the things that makes this entire system that you're about to learn about so different. And so what does this mean? Well, if you love performance, if you love kernels, if you love GPUs, if you love hardware, if you love enabling new things, then you don't have to be a compiler engineer anymore. That means that if you have a performance problem, you're not sitting there staring at compiler IR. Guess what? I love compilers. Even I hate staring at compiler dumps. Like, that's not the way that normal software is programmed. You should not have to do that. This also means, just like I showed you with Vectorize, you can invent new optimizations in library code that don't exist in the compiler. And so you don't have to change the compiler for new instructions, which we'll show you in a second. This also means that if something's in your way and it's not working right, you can just ignore it, because libraries are great. If you don't like them, build a new one. Ignore them. Go all the way down to the metal. Do it in assembly. You can totally do that. There's not a thing between you and success. It's just tools that you can use to be productive. And so this approach is a very different philosophy from what many other systems have done. But that's all the high-level framing, background, context. Now I'd love for Abdul to dive us into a bunch of very concrete examples and show you something that looks much more like GPU code. Abdul?
All right. I guess, like, before we go to do, we had a whole bunch of questions in chat, so I think it might be like a good idea to batch them. So Chris, I'm baiting you here a bit, but like,
go for it. Bring it on, Mark.
One way I've seen people sort of do bootleg compiler engineering is like string-based metaprogramming. So like you effectively use like Jinja templates. I think even in Python 3.14, there's now T strings, which basically are sort of built-in support. You can like look at it. It's, there's not much. You can like look at inputs and outputs. I've seen a lot of repos sort of get started with basic metaprogramming with this. Like, what is the problem with this approach?
So it's not a problem. It's just trade-offs, right? And so there's no magic in the world. It's not. I can't tell you that everything is perfect if you do one thing. As you say, the great thing about templating and stuff like this is it's super easy to hack, and it's in your control. You can see it. It's directly in front of your face, and so there's lots of great advantages. But you're not going to have a debugger that maps back to source code well. You're not going to have. You're going to have all the problems that come with that also. And so what Mojo's philosophy is saying, okay, well, when you do that, Mark, you're becoming a compiler engineer, right? And you did that because you wrote the thing for bfloat 16 and now you want to make it also work for float 32, right? But if you're a kernel engineer doing that, you're making a bespoke compiler for one use case, and that's not the best way to be spending your time, right? And so what we're doing is we're saying, let's give you the ability to build high power libraries, which Abdul will be showing you soon, that give you the ability to compose. Because when I've seen people do that, again, there's many of these things, I haven't seen them all, but what I see end up happening is one amazingly powerful kernel engineer builds a little mini ecosystem around their crazy preprocessor, and then nobody else knows how to use it. And so as soon as they leave the team or company or whatever, then you have to rewrite the whole thing. And so that's not a scalable way for industry to work.
Like I guess like a related question to this is a question coming from SR2357. So like, how would you feel, like, would you like to see an industry standard ISA that captures like more aspects of GPU hardware? I guess maybe this is like a RISC-V question. No, okay.
No, I'm the opposite. I'm the hardware maximalist. I think that if you constrain hardware, then you lose a lot of the power, right? Because here's the way I look at it. With the consolidation around TSMC, what it means is that everybody has effectively the same physics to work with, at least if they're willing to spend all the money to get on the latest process node. And so to me, innovation in hardware is driven by people doing different things, like specializing in different ways, focusing on different niches. And so I'm not the, we need to go back to the days of x86 and having one architecture. I'm in the category of unlock the full power of the hardware and make it super easy for people to be able to talk to the full generality of all the crazy chips out there. So, and I'll say we're in early days right now. We're just talking GPUs, but give us some time.
Yeah, I guess like another question is like, so it sounds like you're not really using much of the CUDA ecosystem. Like presumably you're not even using things like the CUDA toolkit, for example, at all.
Correct. We don't use cuDNN. We don't use TRTLM. We don't use VLLM. We don't use PyTorch. We've built an entirely new ecosystem, all open source. Check out our code.
All right, Albin, do you have any questions?
Yeah, another question in the chat was, how would you compare Mojo with SYCL as you know, in the C++ world? And here you're in a completely new world.
Yeah, SYCL, OpenCL. So I'm very fond because I helped build OpenCL. SYCL has several problems, and I wrote an entire blog post about that too. Go see Democratizing AI Compute, shameless plug. There's several problems. One is all the C++ problems. So I don't love std tuple. So like, all of that kind of stuff, compile time, like all this kind of stuff. The bigger problem with OpenCL is all the fragmentation. And so there's many different implementations of OpenCL. They're all slightly different. They're not actually compatible. The driver ecosystem, all this kind of stuff, it's very difficult to write actually portable code because there isn't a single implementation. If you read the blog post series, I fess up to the fact that was partially our fault, because we contributed a standard, not a reference implementation. And so the entire ecosystem was fragmented. And as a consequence of all the hardware companies fighting each other, they held guns to each other's heads and stuff like this. What happens, we got all these crazy extensions. And so SYCL and OpenCL have all these incompatible extensions from all the vendors. And guess what? You have to use those extensions to get performance. And so at least last I checked, SYCL hadn't standardized a Tensor core. And so if you want to give up basically all the flops on your accelerator, maybe it's okay. Web GPUs, same thing. It's like, okay, well, if you don't want to use Tensor cores and get all the flops, well, it's cool. But if you want to get peak performance out of your B200 or something, well, then you need a different technology.
And I guess part of what makes the flexibility interesting is, like, I mean, a lot of people in chat are asking things like, well, how hard would it be to add like support for like a custom hardware, like, I don't know, Qualcomm DSP or Apple hardware? I guess, like, considering there's a hackathon coming up soon, like, do you, for example, predict that like, like a smart dedicated engineer could spin up a new hardware backend on the big O of how many days, for example?
So I'm trying to be very grounded on this is what we have available today, but I will tell you some cool things. So Abdul will talk about it later. We implemented all of our H100 support in a couple of months, including all high performance kernels, flash attention 3, like all this crazy stuff. It's all open source. Go check it out. Full history. Like, you can go see it, right? And so The entire point of what we're doing is two-pronged. One is enable and solve today problems, but also build into the future. And so in this talk, I'm not talking about the future. I'm talking about today. And so like I am very much a hardware nerd, but let's talk about today. And I don't want to overpromise. I don't want to like that's what everybody does in AI. I want to be very grounded on what you can do today.
All right, and last question, just because we've received this a lot in chat, has been sort of details around your question. I think there was some confusion about like Apache versus like a bespoke license. I'm sort of curious, at least for the programming language, like what you showed us, like we want a programming language to make GPUs faster. Like what is sort of the state of the license of this language?
Yeah, so we'll get to that at the end. And so we have a whole thing on usage license, and it's free. But but so it said Apache LLVM Apache 2 license. Just to disambiguate that, the LLVM part of that removes restrictions from Apache. And so it's more liberal than Apache 2. It gets rid of like the binary attribution clause and a GPL v2 incompatibility. And it's the same license that LLVM is used for. So if you like LLVM, then presumably you're compatible with this thing. So
all right, excellent.
Cool.
I guess without further ado, maybe we can do the transition.
Thank
you, Chris.
Sounds great.
Can you see my slides?
One moment. Yes.
Okay, awesome. So we're just starting. So we're actually going to go into the more technical side of things. You know, like Chris was talking about what is present today. I'm going to actually dig deeper. I know like folks here like to nerd out and look at assembly and so forth. So over the next few slides, I'll be talking more about Mojo and actually answer a bunch of questions that I saw kind of stream through the chat as well. So the main thing is Mojo unifies everything. So Mojo is more or less all you need. So I don't think Chris has showed any GPU code before, but this is GPU code. So this is unifying CPU and GPU code. So say hi, I don't know if you see in my mouse, but say hi is a function that I've defined, and I can call it say hi 42, works fine. This is CPU launch, but I can also say call it with a GPU function with griddim1 and blockdim1. All of this, and you can go to the modular, you know, everything here. These are links. You should be able to go to these to actually try this today, right? So we're telling you just you can download it today and just try it, right? We're not, again, as Chris mentioned, we'll love to do a vision talk at some point, but this is not the talk for that. But this is how Mojo GPU programming looks like. Now, it's also like portable across all hardware and software. So for example, again, one of the tenets of Mojo is everything is implemented in the library. So even integer and Boolean are library types. They're not, the compiler more or less does not know anything about integer and Boolean, which means you can define everything in Mojo, right? So here is a definition of exponent exp2. So it works on SIMD types. So SIMD is first class type. You know, SIMD has been around since the 1995 or so. So it's been 30 years. It's kind of interesting that many languages don't even have SIMD support, and even extensions to support SIMD are few and far between. Now, the other interesting thing, which is, Chris mentioned, is here we have a polynomial evaluate, but we use list. And because it's in between these square brackets, this is compile time evaluation. So this list has 0, runtime overhead, but it's a nice way to encapsulate some sequence of digits, for example, in this case. Now, this is valid. This is a mathematical definition of exp2, but there's also a bunch of ways you can actually optimize it even further, right? So, for example, for Hopper architecture, you can use the x2 instruction, and you can call it for if you have a single F16 type, you can call it, but if you have 2 F16 types, there's a different instruction. So this is calling a PTX intrinsic. And the same thing for, if you're bfloat 16, you can call it in a different way. But the point is that we've abstracted away, a user calls exp2, they don't know what the internals are. This is a unit of abstraction that folks do that. Parameter here, when you put parameter if, this is similar to a compile time if statement. So, if you're in C++, it's similar to if const expr, right? And then, this, everything here is written in Mojo. There is no, there's nothing special about this code. Even SIMD type is written in Mojo itself. Type is written in Mojo. And this is how you write this call PTX intrinsic. So what this is saying is, if the SIMD width is 1, I'm going to call this scalar function. Call this function. By the way, you can pass in strings as kind of parameters, right? So think about the pain one has to go through to pass in strings as template arguments in C++. You can also concatenate strings, right? I think there's ways to bend C++, so you can do string concatenation. Here you just call plus, right? And this is saying that if your SIMD width is bigger than 1, just decompose it into a sequence of 2 wide SIMD types. So it handles the decomposition of if I have a SIMD of 4 elements, it will put 2 elements at the same time, and it would call that. And if I do parameter 4, it means unroll the loop. And this is not a compiler hint. So I know Chris showed the pragma OMP vectorize, which is is more or less like a compiler hint, or pragma enroll sometimes is a compiler hint. This is actually a Mojo will not get in your way. If I say parameter 4, Mojo will unroll the loop, and it trusts you, right? So we want to bring power to the kernel engineer, which also means if I unroll the loop and the loop is 10,000 elements, that means it's going to take a while to compile, right? So that's kind of the pros and cons, right? So it gives you a lot of power, but you have to use it as well, sensibly as well. So none of this is special code. None of this is I have to change compiler. I have to go change my frame of mind when I'm working in C++ and Mojo and so forth. I'm always thinking about Mojo code. I don't kind of shift my mental mind, right? Which means also everybody's staring at the same thing. They're not staring at 5 different files, 5 different languages, and so forth. And of course, when you want to add new support for new hardware, you can do that. So again, we're picking on this exp2, for example, here. But for exp2, what we could do is say, extend this thing to, if you're on AMD and your D type is F16 or float32, call this LLVM intrinsic. So F16 and this other intrinsic, the string, what it's called is if you're F32. And again, why we're picking on exp32, well, it's because it's actually used in attention. The softmax contains exp as a core component, and exp can be implemented in terms of exp32. The other thing that's kind of super interesting is you have access to all the LLVM intrinsics, which there's thousands and thousands of LLVM intrinsics that are built by the hardware vendors, right? So everything is available for you. And you can actually, in a bunch of cases like this, in this case, this hardware intrinsic does not support SIMD width, but you can make it so that the exp2 function supports arbitrary SIMD width, right, by just unrolling the loop. The other thing is, familiar syntax, right? So, if I do D type in float16 and float32, this is familiar syntax to a Python programmer. You don't have to say D type equals float16 or D type equals float32 and things like these patterns and so forth. You just kind of write the code in a natural way, which actually bridges the gap between your mental model, but also the researcher mental model. Researchers think in Python terms. They don't think in C++ or CUDA terms and so forth, right? And, as it will, I know folks' minds are being blown at this point, but we'll show results that, you're getting these things without sacrificing what kernel engineers care about. And by the way, I'm a compiler engineer, kernel engineer, et cetera, et cetera. So I want to make my life easier as well. The other thing is portability. So I think there was a bunch of questions about, SYCL. And, before that, there was like C++ AMP and other things. We want to also bridge the gap between GPU programming and CPU programming. So I'm picking on this for each function, which is an element-wise operation. So on CPUs, element-wise operations, what you need to do is chunk this domain into n chunks, and n is usually the number of cores on your system. And within these chunks, I'm going to write code that evaluates the function in a vectorized manner. So Chris showed the vectorized code, and this is, on CPU, that's what you do. You vectorize a loop per thread, and then you run it multiple threads. On GPU, it's a different strategy, right? So this is the point of you choose what abstraction, at what level of the abstraction you want to pick on. So on GPU, you might say, well, I'm going to do thread index.x, or I'm going to launch number of SM blocks and partition code based on that. You also want to do vectorized loads and vectorized stores. You want to use the LDG instruction on GPUs if they're available and so forth. So there's a lot of code behind the for each, and it does a nice heuristic based on your problem that it gets, that you're doing. And as we'll see in the next few slides, this is not magic. This is not compiler wizardry. We'll show the code for this. Now, the other thing is folks really want sometimes to just express what they're maybe familiar with CUDA C++. They just want to translate their code into Mojo. So Mojo does not block you from using CUDA C++. In fact, the for each function is written using primitives similar to what you'd see in CUDA C++ or Cub and so forth. We're not using any of that. We've built all of this ourselves. Like we don't use MVCC, for example. I think Mark had a question about that. But you can say, run this out, add one impl, and well, there's a typo here. It should be adding one, but that's okay. So it's kind of interesting. But there's another kind of interesting thing here, which is input. Output. I'm not passing output. Actually, there's another typo, which is output should be here. But I'm not passing output. I'm capturing that. So this is a closure function that's being captured, and I can then sort of build things in a compositional way, right? So I can do partial functions and so forth. But this is very similar. You say launch it with block size, and then grid dims is, seal div and so forth. And then the other thing to notice is there is no this is not a DSL, so I'm not saying from something import seal div. I just say from math import seal div. That's kind of it's the same seal div that is available in regular CPU code that I'm using here as well, right? Now everything in Mojo is JIT compiled, which means you get the best executable or the best run on your hardware. And there's also no emulation. So warp size is 32 on NVIDIA. It's actually 32 or 64 on consumer grade AMD. It's 64 on enterprise AMD hardware. SIMD width, warp size picks the right value, right? So there's no, it's always 32 to do emulation and so forth. And same thing for SIMD width. You have AVX 512. That's a SIMD, 512 is a SIMD width. But if I go to Neon and GPUs and so forth, 128 is a SIMD width, right? So it kind of, the program, by running it, it adapts. And by making everything parameterized, you get the best of everything. Finally, the issue with JIT usually is slow compile time. I don't want to wait 8 hours for the thing to compile. We care so much about compile time. We spent so much effort on making Mojo, LLVM, and so forth, MLIR, use every process available, use every core available, use caching and so forth, so that In fact, when folks run Mojo, it has if I do Mojo run some file, it's as fast as doing just Python the file, right? So that's how you get kind of the benefit. Folks don't have to wait like, oh, it's going to take 1 minute to compile or 2 minutes to compile and so forth. And then the other thing, that folks care about is performance, right? So you have complete control over the code that's being generated, right? So we lift all the things from the compiler to the library, which means you can, let's say, async copy, you just have to kind of write what the implementation of async copy is. It might use LVM intrinsics, you might use inline PTX and so forth. And you have complete access of the entire GPU hardware, through LVM, MLAR, inline assembly intrinsics, and so forth. Now, you also get zero-cost abstractions. So language features like closures, exceptions, traits do not add any overhead. So you get the abstractions, you get the nice things without paying for them, right? Which is, I know there's like no free lunch, but this is getting as much free lunch as possible. Now, I want to kind of nerd out about for each, which is also called element-wise, and show you how it's kind of implemented. I'm not going to go very, very deep, but you can go into the code. So this one is just doing an element-wise exponent. So for every input element, it computes the output. Output element is the exponent of the input. I could say it's a target is GPU. I can give it a arbitrary dimensional space, right? So I can give it whatever I want, and it would just run. Now, element-wise is nothing special other than it's a function that's built into the library. Here's the, it's kind of an implementation. You can actually go to this file and see the full implementation. But, for the GPU, it says, oh, thread index is, TID is thread index.x plus block size times block index.x. It handles PDL. If folks are familiar with Hopper and so forth, it will do PDL for you. It then has heuristics on how to partition the data, how many grids and things like that to the block. Now, highlighting the thread index.x, because thread index.x is also not special, right? It's just a library type, right? So thread index.x, it's, you get this nice thing about in Python, getAttr just gets you the property of that struct. And it says, if you're on NVIDIA GPU, well, get this intrinsic and plus whatever this dim is. So this could be .x, .y, .z, so forth. If you're on AMD, you get to, you generate a different intrinsic, right? So that's how things work. And then as you kind of add, if you want to support new hardware, you just kind of augment that and so forth. And we're going to be adding more features to Mojo so that it becomes easy to kind of extend these things to other hardware as well. But this talk is not about the future; it's about what we have today. But the point is, you can kind of drill down from these high-level constructs and go, deeper and deeper and deeper, right? So if I want to change what element-wise, like the heuristic for element-wise, I just change the element-wise function. I don't change the 500 places that the element-wise is being used, right? Or if I'm, April Fool prank or something like that, if I want to say thread index.x is really block index.x, I just go and change these intrinsics, right? Obviously, things will break, but the point is that we want to give the kernel programmer who are sufficiently smart full superpowers. Now, this is how you'd write C++, kind of more high-level code, but you also have a lot of features in Mojo that are kind of unique, that give you a lot more flexibility. So one feature that I want to pick on is traits. So traits are, you can think of them as interfaces in Java, if you're familiar with Java, or protocols in Swift, and Go generics and so forth. I mean, they're not one-to-one correspondence. You can actually go to the documentation. They have, docs.mojo.com has whole sections on what traits are. But I want to pick on this because it comes up when you want to do attention. So if folks are not familiar with attention, it comes with a different, there's many faces of attention. You have causal attention, sliding window attention, chunked attention, weird variant of attention. What we want to do is just define a generic attention kernel and then say, okay, I can customize it based on certain properties. So here I can say trait MHA mask, and it has a mask function and then a status, whether it's fully masked, partially masked, or no mask at all. And a concrete example is, I think 2 weeks ago, 3 weeks ago, Llama 4 was released. It introduced a new type of attention called chunk mask attention. This is the pattern that chunked mask attention is. So what we need to do is just define a chunk mask attention, and we can then use it in our MHA kernel. So the MHA kernel, the multi-head attention kernel, actually takes an arbitrary attention. So this is the code that does that, and then applies it. And then I can just kind of make a chunked attention kernel instantiated if I wanted to, and I can define the local window size, as a parameter. Now, this means also like I can kind of customize these things, make the code more succinct, keep the algorithm clean. Don't put a bunch of if statements everywhere in my attention code, which is already, kind of complicated already. I want to make things more composable and so forth, and I want to be able to do different attention masks. And by the way, if you go to the MHA mask function, it also defines combinators. So I can say or mask or and mask, which takes like two masks and then composes them together. So you can kind of say, oh, chunked mask causal, and you just take the causal mask and then and that with the chunked mask and just create a new mask type together. This is very, very hard. And if you look at what others do, usually they kind of reorient their inputs so that you get the effect of chunked attention without actually implementing it yourself. But it incurs a bunch of runtime overhead as a result as well. Now, I think, do we have questions? I'm gonna jump into a different section, but I wanna pause a little bit, maybe Mark or
So Chris is racing you because he's answering all the questions in chat so far. So we're not gonna need to read out the answers.
Okay,
you should keep going, yeah.
Okay, so we've been talking about.
I'll ask some. I'll bait Abdul, right?
Okay.
And I think you talked about this a little bit, but come back to Mark's question of how do you implement, the DeepSeek people figured out some undocumented PTX instruction. Like, how do you add support for that to the compiler?
So you wouldn't add it to the compiler, right? So when we say, so let me say something that, again, will blow people's mind away. Mojo has no clue it's compiling for GPUs.
It literally doesn't.
It has no idea, right? It's it's the same logic for CPU as it is for GPU. It does not understand GPUs. Everything is put in the library. So when I said, like, I don't know which slide was, thread index.x is not a concept in the compiler. Launching a GPU function is not a concept in the compiler. There is no like triple brackets and stuff like that. It doesn't exist. The parser does not, we don't have these things in Mojo. So it has no clue. So if we want to add what DeepSeek is, what DeepSeek was doing, you just kind of, sorry, I'm going through slides, but you just add the inline PTX or the LLVM intrinsic, or you kind of say in the library, replace the sequence of operations or this binary with this other binary and so forth, right? So
okay, Abdul, but then how do you implement some new scheduling algorithm that you want? How much do you have to change the compiler for this?
0. So again, we don't change any of the compiler. By the way, you should be able to, again, you don't have to trust us for any of this, right? All the code is open source, full history. You can check H100 bring up or A100 bring up, or even like the first GPU function, how much we change the compiler. And the answer is none, right? A lot of folks that are writing kernels or writing these code, many of them don't even know C++. Definitely most of them don't know compilers, right?
Yeah.
So again, this is saying the intersection, because finding those people is very rare. You're trying to find a person that knows kernels and compilers, right? They're different departments, different fields, everything, right? And then you also would love the person that's the kernel developer to also understand AI. So to find that sweet spot, there's only dozens of folks in the world that have that intersection point. So the
entire point is don't put it in the compiler.
Right. Yeah. So not even integer, not even this address space shared or unsafe pointer is a compiler construct. Even this constraint is not a compiler construct.
You can go look at the source code for pointers and address spaces. Right. Kirill's asking one. I'll take it. Hi, Kirill. You're asking if you thought Mojo has a borrow checker like Rust. How does that work for GPU programming? So Mojo does have a borrow checker. It is in the same space as what Rust does, but it's evolved because Rust is also 15 years old or something. And so you get memory safety, compile time, memory allocation checking, exclusivity checking, read exclusivity, blah, 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 or modify exclusive or shared, all that stuff also is all in Mojo. We're not talking about today, but guess what? You don't want a garbage collector in a systems programming language. And so the entire way that memory allocation works is predicated on having a really badass memory management system that's safe. And so we're not talking about today because we're just focused on GPU programming, but it all works on GPUs because you don't have dynamic memory allocation and things like this. Though Mojo does talk to C and Mojo's a very friendly language. So if you're on a CPU, you can talk to Python libraries, you can talk to C and call malloc, you can do whatever you want. You just get an unsafe pointer back and things like that.
Actually, Chris, that's a good segue into a question like Albin gave me before he had to leave, which was how does Mojo interop with the rest of the Python language features? Specifically when you're dealing with Python implementations that are not C Python, you have to deal with arbitrary C. Yeah. So.
So we don't talk about just given the venue, we decided to focus on GPU stuff, not on Python ecosystem. But Mojo is very strong on CPUs. That's a huge thing, by the way. On CPUs, you have Python code, and you have C and Rust and C++ and all this this ecosystem out there. It's very important that Python and Mojo talk to each other, and so you can do that in two different directions. You can import an arbitrary Python package, and it just works in Mojo. And that works by using the CPython interpreter to run that package. And because the syntaxes are the same, you can just use it. It just works. It's pretty amazing. And so you can go import NumPy or PyTorch or whatever you want. You don't have to rewrite code or make it Mojo compatible. It just works. No FFI or bindings or none of that kind of stuff. A new thing that we haven't fully announced yet, it's public within our community, is the ability to go the other way, which is say, I have a Python package. It's slow. I don't want to rewrite code in C and do FFI and blah, 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 and PyBind and et cetera, et cetera. I just want to take a blob of these for loops and put them in Mojo and have it automatically bind. And so we're completing that now. This will be out in the next month or two-ish, something like that. And I'm super excited by that because that means that the most commonly requested feature for us was, hey, Mojo's 30,000 times faster than my Python code for this numeric thing like tokenization or whatever. How can I just put the fast performance critical code in Mojo and just still vend a Python package into my ecosystem?
Well, that also make PyTorch interop stuff much nicer, I guess. You were hinting at that in chat. Okay.
Oh, totally. Well, and we use this in LLM serving. In LLM serving, it's really important to have really high performance CPU code that's interoperating with GPU code, and this is really quite critical for heterogeneous computers. And so again, we decided just based on the context here that we'd focus on GPU programming and explode some brains around metaprogramming and things like this, but this is really quite fundamental work. And again, we've replaced that entire Gen AI stack all the way up until like LLM serving and things like this. And so in our repository, you can go check out our page attention, radix caching, and blah, 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 all that stuff too, all written in Mojo. And so like, please check it out. We're not gonna be able to talk about all the cool things, but there's a lot of cool things. And I know that people think we're like, it's too good to be true or something, but don't believe me, go do it. It's fine, download it. Like that was the whole framing.
So Chris, actually, another trade-offs question, which is
yeah.
So it sounds like a lot of the stuff you guys were talking about here. A lot of these seem like this is going to be like a JIT-like approach. Sorry, like not a JIT, like a JIT approach. So like typically the trade-off there is like slightly slower cold starts, but like, you know, the binaries are small, but you also need like a local tool chain. Yeah. My sense is the community is moving towards JIT despite the trade-offs, but I'm curious if y'all could both comment on your take on
it. We fully support JIT and AOT, but Bill, you want to talk about this?
Yeah, I mean, JIT is very useful, but I mean, as you mentioned, JIT, if not implemented correctly, JIT can be very, very slow, right? I have no patience of waiting a minute for some code to compile, right? I have no patience to wait 30 seconds, 10 seconds for a very complicated piece of code, and we'll show some, like a attention code, is what I'm comfortable with. Even then, we're constantly a never-ending effort to bring that cold start from 10 seconds all the way down to 1 second. Currently, for folks, I mean, just to put a little bit, again, a lot of folks, will say this is untrue and so forth, but please try it. Today, we can compile Llama 7B with cold start in under 1 minute, right? And this means I'm compiling all the way down, right? The integer is being compiled
from Python, from Python,
right? So from Python.
This is not like you export a graph and then run a little compiler thing. This is like the model.
So this is synthesizing kernels that we've never written, right? Doing fusion, and we'll talk about it. By the way, for folks, we're halfway through the slides, so folks, since minds are being slowed with,
I think we're
a little bit. So compiling like I think it was like 1 million lines of PTX in under a minute, right? Synthesizing those 1 million lines of PTX, but also compiling it in under 1 minute. Right,
okay,
and then
obviously, Bill, can I'm trying to resist because I'm beating up on compiler engineers in this talk, but can I be a compiler nerd? Is that okay? Sure. So when building an entirely new language in 2022, 2023, 2024, right? There's an entirely new category of compiler technology like MLIR that you can build on top of, right? And so I know a little bit about LLVM, both the good parts and the bad parts. And so this is an entirely new epoch of tech that didn't exist. And so somebody's asking about how we use MLIR. We don't use any of the MLIR dialects. We don't use linalg or arith or like any of that stuff. We've built an entirely new category of technology that didn't exist before. This isn't we took an open source thing and forked it and hacked it up a little bit. This is like, we do use LLVM and MLIR core, but we don't use the dialects. This is like an entirely new thing. And so this compiler that Abdul was talking about that generates code, 100% parallel. So it's like actually uses multi-core, right? That's actually a big deal. LLVM couldn't do that for a variety of reasons. Well, we fixed this, right? And so there's an entirely new category of technology that we're talking about. And we don't have time to deep dive into that. We're talking about how to use it, but this is extremely deep nerdery. So this is actually a new creation entering the world. This is not, again, a DSL somebody hacked up over the weekend. This is hundreds of people years worth of work.
Yep. The other thing is, we give regular, folks that are interested in compilers, we gave a lot of what we did for Mojo at the LVM dev meetings. There are videos all online. Please go that, but this is not the talk for that. I mean, I think
exactly.
We need to
learn about closures and many other very great nerdy things, and there's many talks there.
Right. Async was another one that we gave a talk about, but again, different talk will do more in the future, right? Now, the other thing I want to, by the way, pick on is borrow checker. So borrow checker is interesting because, I mean, what a borrow checker is, it's not really too much about memory. It's about like, I'm going to init at some point and I'm going to call del at some point, right? So you can do whatever you want. It's not just malloc and free. You can say, oh, synchronize on the del operation, or do something completely different, right? So again, this exposes new programming paradigms that were not available to you before. And this is also, again, I'm not going to talk about it, but it's not similar to RAII and C++ and so forth. There's
this is a new category of tech. So, but let's keep going.
Okay, let's keep going. So
GPUs are cool, man. Come on.
Yeah. So tile-based programming. So I know folks have heard of matrix multiplication, attention, et cetera, et cetera. They're very, very important, right? Folks write compilers specifically to matrix multiplication compilers and attention compilers and so forth. Now, the problem with that to kind of implement it in CUDA, though, is there's a missing abstraction. SIMT is great for, kind of more or less like straight line code. When you start saying, oh, warps and so forth, it kind of starts like you have to bend your mind and so forth. So what, in some cases, there's a huge class of operations, matrix multiplication and attention and derivatives of those are very, very important for AI workloads. So we actually want to make sure that the kernel developers are also productive, right? We don't want them to reinvent the wheel like 50 times, right? You can invent the wheel once, and then you want to use it. Like, you don't need to invent it again. Now, again, I mentioned there's compilers for that. We want to put it in the library. Cutlass did an amazing job that proved that a library-based solution is perfect for this. The problem with Cutlass, and Cutlass has a lot of great ideas, is C++. And again, I'm a C++ user, but I don't like std enable if t and things like that, right? So this is an animation that's showing how each block can be, tiled, and then you can subdivide these tiles, you can vectorize these tiles, and you could do operations on those tiles. There's an entire tutorial on how to do operations on that if you're interested in that. And what that means also is you can start thinking about things from a tile-based perspective, right? I want to load this tile, load this other tile, do some operations on it, but maybe loading the tile, there's an abstraction where there's things like TMA and other kind of asynchronous copies and so forth that I can leverage, but I don't have to re-implement those all the time, right? I just hide the abstraction, hide the the hardware-specific detail behind the tile-based abstraction. And layouts are parameterized, right? So, by the way, for folks that are that don't know what layouts are, it's essentially fancy ways to do index computation. So, if I want to find the position, I do it in a more natural way rather than linearized indices and weird shifts and shuffles and swizzles and so forth. This is a more natural way, and it was pioneered by folks on Cutlass and Qt and so forth. So what a layout is a data layout and then an element layout. So what each element is, but also how you access each element. So it's a function from ND coordinates where that's how you think. You think matrices are 2D to linear coordinates, which is how the computer thinks, right? Computer thinks just like address 0 through address whatever 2 gigabytes or whatever the thing is. You can again, none of this is compiler magic or wizardly. All of it is defined in the library. You can go to this file, see the full implementation. It's not hundreds of thousands of lines of code. It's like a few, 1,000 or 2,000 lines of code. It's the same definition that you're familiar with if you're familiar with Cutlass and Qt, but there's also extensions that make it easier to do that. And you actually can debug print the layout, which is very hard if you're in the, I don't even know how you can print a template. Like if I'm doing a std tuple and template argument, C++ does not provide you with tools to do that. Now you can say, do static assert and then put it as the third argument or whatever the thing is. and that's the way. But that's not the natural way, right? You're kind of bending the language into areas that it's not like forgiving for you. The other thing is it's slow to compile, right? So that's the problem with C++. Now here I'm showing this. So here's like an animation of how, if I have a 4x4 matrix and stride 4x4, I can sort of subdivide it. I can say, here's my domain, here's my range. I can change it to column major instead of row major, and so forth. Right. So please go to the docs and they'll talk about it again. If we can spend like hours on this thing. This is like 4 or 5 slides. And you can make complicated layouts. So you can say, I'll have this block, I can subtile it, I can then rotate it slightly, I can do a swizzle, I can do blah, 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 and so forth. Again, things like OpenXLA, Erie, other compilers, they have similar ideas, but the problem is it's hidden away in the compiler. And by the way, layout for a CPU might not be necessarily the best layout for a GPU, and definitely like the setup that you do for A100 is not the best way to do it for Blackwell and so forth. You can also like visualize the layout, right? So folks can stare at these things, right? But you can also say print these things. This is familiar for folks that are familiar with Cutlass. This should not be super, super complicated. Now, folks can, you can kind of geek out about the mathematics of all of this and how this is an algebra and so forth. But at the end of the day, we're pragmatic. We want to use these things, right? We build these things because we're the users of this tech. Now, going back to abstractions, you have to choose what the level of abstraction is, right? So do I put one big ass function and put 5,000 if-defs in it, or do I just say, well, these are just 2 different functions, right? And what we say is, okay, there's different pipelining strategies for different hardware. So on an MI300 AMD system, the best thing you can do is double buffer, right? So you say, I'm going to load this tile, and then I'm going to work on the prior tile, right? And just do that. A100, you have async copies. So I could say, pipeline the operation, do let's say 5 async copies, and then start processing the latest, the earliest one, right? H100, gives you warp specialization and other operations. Blackwell gives you another set of operations and so forth. So what we want to do is kind of unify everything, unify what we can, but also acknowledge that there is fundamental differences between the two. And by the way, we're not interested in the 90% of soda. We're interested in being soda. So that's another distinction between Mojo and others, right? So I want to kind of delve into real code, right? So not that everything we've shown you is also real code, but this is Matmul. This is like the thing that folks spend PhDs on, right? And this is the implementation of Matmul in Mojo on MI300. Now it's highly abstracted, but that's kind of a plus, right? So this is the plus of Mojo is you get the abstraction. You don't have to write the same thing 50 times, copy paste the same code. I know like there was a talk about using Jinja and all these things, which is like, essentially it's a programmatic way of copy pasting some code, right? But this is the code, loads from RAM, it does a barrier, loads some other double buffer, then does the, main loop. This is like I couldn't put the entire thing on one screen, but this is the entire matrix multiplication code. And this is production code. This is not, even though it looks like pseudocode, it's not pseudocode. This is what we use. I'll show also performance later on. And again, please keep in mind that this is the code that we're going to show perf on later. Now, none of this is magic. So we're saying MMA here, but MMA is just a function, right? So MMA is defined as part of this layout tensor. So I say tile this operation by the number of MMAs, the elements per thread, vectorize the operation, then do the matrix dot product, right? And this is going to use tensor cores. whatever is available on the system, right? So you have to parameterize everything, but the point is that you get the tensor cores. The other thing that's super interesting is like all of this is hardware agnostic, right? The implementation, like how you instantiate this, is hardware specific, but the layout, algebra, all of that is hardware agnostic. So it works on CPUs and GPUs, right? It's actually useful to debug certain things, visualize the primitives on CPU, right? I want to do print the thing or print the SVG or the visualization of the layout. Use GPUs where it's good at, use the CPUs where it's good at, but also unify things, right? So as Chris mentioned, like, I know this is a GPU talk, but there's a CPU side that's driving everything. There's a bunch of pre-processing and post-processing that could leverage the system, and having a unified library is very, very powerful. We're also not going to be talking about like performance of CPU, but we have soda perf on CPU side as well. And you can also define like, okay, here's my tensor core operation. So it takes a accumulation type, what the A type, what the shape is, and whether it's a transpose or not. And then you can use the Python @ symbol, which eventually calls their mathmal function. And all of this is like GPU agnostic. There's many things that are GPU agnostic, and you just leverage them. There's nothing special about AMD, NVIDIA, CPU, et cetera, like tile is the same algebra, vectorize the same algebra, loading is the same thing, and so forth, right? It's the primitives that change, right? Am I calling WMMA on Hopper or TCGen version 5 on Blackwell? The other important thing, and again, a lot of these things are the composition, right? So building on top of things, because we have a very strong parameter system. It means everything that could be compiled at compile time, or could be evaluated at compile time, does get evaluated at compile time. So a lot of these things desugar into like an offset, right? Some integer that gets resolved at compile time, right? So you have zero runtime overhead, right? Now, again, this is you can go look at the code. We have also tutorials on how to progressively implement a more complicated matrix multiplication. But the code on the right is real code and is just doing shared memory matrix multiplication with register tiling. And this is the full code, right? Does thread index and so forth. Again, you can use abstraction. You can not use abstractions. You can use this tile tensor. You can not use it. Tile tensor is implemented using primitives. You can go directly to the primitive if you want to. Nothing. You can implement your own layout tensor, 3D, whatever, like ND, hypercube, whatever you want. Nothing is stopping you from that. So we want to kind of make it so that you're able to explore, able to invent new things, right? And if you're not in the AI domain, if you care about, weird data structures and so forth, we want to give you superpowers to be able to kind of put whatever you have in your mind on paper versus, being shackled by, oh, this is a DSL that only handles this domain or something else. Now, the other thing to cover is, if you kind of take a step back, kernels are part of the puzzle, right? Kernels are meant to be composed. There's something before and something after, whether it's like post-processing, pre-processing, some other operation, some other compute, some network, communication, and so forth. All of that is super, super important. So you're just looking at that, matrix multiplication kernel, right? Nobody asks like, I want to run matrix multiplication. They ask, I want to run an LLM. I want to run the physics simulation. I want to, at the heart of it is a matrix multiplication, but there's like other stuff around it. That's super, super important. So again, there's an entire talk that we can do about the graph compiler, but the thing to highlight here is the, this composition, right? So you have like, for example, a graph, like llama and so forth, have a matrix multiplication followed by Siluan multiplication, right? And what compilers do, or graph compilers, usually that's the term that folks use, is they kind of smush everything together, right? And that's Max has that. So Max is the inference platform that we have. We're not talking about that, but has that. But the issue with the fuse everything approach is you get an operator explosion problem. So let's look at Silu, for example. So Silu is really x times sigmoid of x. Sigmoid is defined as 1 over the exponent of this equation. So instead of this is 1. So this is Silu is this equation. Now I can go with 4 lines, implement a kernel that does Silu. But what's better than a kernel that I write is a kernel that I never wrote. And that's kind of a fundamental thing, because I can never write, some new paper comes out tomorrow, Silu 2 or square root of Silu. I'm not going to go in and stamp it out every time. So what you want is you want to define the primitives. Silu is just defined as plus, the components are plus, divide, exponent, negate. That's all you need. And you want things to kind of synthesize new kernels for you. So what you want to do is define puzzle pieces and something that says, okay, fuse everything together, get the best possible implementation, and so forth. And that's what Mojo and Max do as well. So you don't have to worry about like 2,000 ops, right? And that's why, by the way, that's why if you go to the repo, you don't see Silu as implemented, right? Because we just define these primitives. It's up to the other parts of the stack to kind of synthesize Silu for us, right? Which means the job of the kernel programmer becomes much, much easier because there's no 5,000 things to maintain. It also means that, again, a lot of math is, there's like a finite amount of math operations, right? Trigonometric functions and so forth. If you just implement those primitive operations, like first chapter of the calculus book or things like that, I'll be golden because nobody's gonna, define like some weird operation. Same operations that existed in Euclid's time probably still exist today: add, subtract, multiply, and so forth. It's not like a cutting edge science. It's just a composition is cutting edge, right? So so if somebody writes ReLU, which is max, it just kind of decomposes the max of x of 0. So ReLU 6 becomes like max of x comma 6, right? I don't have to write ReLU 6 and ReLU and so forth. I just have to write max. Right. So GPUs are great. We talked a lot about programming. You can very, very easily do everything that we said in a weekend if you don't care about performance, right? So what we want is all of this plus performance, right? So if you remember the figure that Chris showed is usability, performance, portability, right? Up to now, we hopefully convinced you usability and portability. We have not talked about performance, right? So again, matrix multiplication is an easy problem if you don't care about performance. You just write 3 for loops, right? You don't use tensor cores. You don't do any of that sort of stuff. What we want is state-of-the-art performance. Now, all of the slides that I'm going to show for performance are still work in progress. We'd love folks to help. You can also try this stuff yourself, right? Don't trust these figures, right? There's, I mean, if and you can replicate everything by just running kbench and the YAML file, right? These are the shapes also for Llama 70B, so we're not picking weird shapes, right? This is what cuBLAS is supposed to be optimizing for, cuBLAS LT or Cutlass and so forth. We picked cuBLAS here because it's the fastest implementation, right? And what you see is, more, we're at close to parity in some cases, beating cuBLAS, right? cuBLAS is state of the art. It's speed of light. We're still working on this implementation, but we also noticed that there are some cases where we're less than ideal. Again, we're still working on this, but we'd love folks' help, right? Now, again, a person can go in and write these things in, different languages and so forth, but what you don't get is portability, right? So this is the performance on MI300. So it's kind of funny on AMD hardware is there's two different libraries, RockBLOS and HipBLOS LT. Sometimes RockBLOS is faster than HipBLOS LT. So what we want to compare is state of the art, which is the maximum of both. And what we want to do is achieve, per parity or exceed the performance of HipBLOS or RockBLOS, or state of the art. Essentially, we take the max of everything. So in many cases, like in this case, we're faster than both. This case, we're faster than both. Other cases, we're not. Again, work in progress. We're working on this. Would love your help and so forth. The other thing to note is, again, backtracking a little bit, mathmul does not exist in isolation. Mathmul is usually followed by another activation block. And the way we've written our matrix multiplication is it accepts an epilogue function that does the essentially post-processing on the matrix multiplication. This is a head-to-head battle against the gem or BLOS BLOS operations, but cuBLOS and RockBLOS and so forth does not allow you arbitrary kind of post-processing that fused into the matrix multiplication. So this is a head-to-head battle, just being fair. But again, in real-world application, it's mathmul followed by something else. We do the fusion. cuBLOS and other BLOS libraries do not provide you the API to do that. So that's also like the argument against, traditionally the argument against libraries is libraries have encode common patterns versus for us, because of the parameterization, we just make it flexible. We make it open. And it's, mathmul is just part of the process. So, we're also interested in SOTA on other things. So this is attention kernel on MI300 showing us versus Triton. Now, up to now, we're showing you code, but there's a human programming this. And what a human wants is debuggers, syntax highlighting, formatters, things that you'd expect from like languages in the modern day, right? You're not using notepads for programming. And you also want to integrate with like existing tools. We cannot invent everything, but what we can do is provide at the compiler level, provide everything that a external tool needs, right? So it also means that you're familiar with the tools. You're familiar with Nsight Compute. You're familiar with ROCm Compute. You're familiar with CUDA-GDB and RockGDB or Compute Sanitizer and so forth. So, and what you could get, and this is kind of going back to Mark's, Jinja and question, is you can see like the PTX, but you can also backtrace it and say what Mojo code is can be attributed to this code. So this is very, very powerful because it tells you like this 3 lines of Mojo code took 90% of the time. Well, now you just go in and optimize that. Versus, a black box where it's like, okay, well, it went through 3 transpilers to actually get to the output. I can actually just kind of, we don't do that. We just kind of get good source location and source mapping. The other thing is, folks don't necessarily have access to, like I'm on a Mac. Sometimes I want to look at and see like what's the output in PTX look like, or what's the output in assembly look like. What I can do is just say, well, I have this add function, and we're picking on add a few times, but I can say compile it for B200, generate this assembly, right? I don't have to have B200 on my system, right? I can be on some Linux system and just run this, or Windows, what is it, the Windows system Linux system for, Windows Linux subsystem. I could do that. And you can then say, okay, well, what's the output for like AMD? What's the output for some weird accelerator? What's the output for CPU? And you could just do that. And you can actually just say Mojo emit LLVM, cross-compile it, target accelerator, NVIDIA, and then the SM type, and then file that Mojo. It just dumps it for you. Okay, this is more for the folks that are interested in looking at PTX and assembly and so forth. Perfectly fine. Nothing is blocking you. There's nothing else. For the regular user, folks are interested in, like using an editor. So this is an animation that's showing how folks write code, right? So here I'm just saying generate prime, run it, produces an output. I can then put a debug statement, see the variables that are being generated, go stack trace and so forth. I can add a log point, say, well, what is the output bound? So I can produce like sensible error messages. I can then say watch statements and so forth, and rerun the code and things like that. This is, practically, maybe 1.5x sped up, but practically real time. Chris, do you want to take over? We can pause also for questions because I'm pretty sure folks' minds are blown.
Yeah, why don't we do some questions?
Okay.
And then we'll get into Mark's hot takes.
All right. Let me see.
So paraphrasing somebody, so you compare to cuDNN, how does it compare to Cutlass?
Right. So cuDNN is,
or cuBLAS, I guess. But.
Right. So cuBLAS potentially uses cuDNN. cuBLAS potentially uses their own compiler. Some poor soul wrote handwritten assembly, right? They say, okay, I'm going to write the handwritten assembly myself and so forth. It also uses Cutlass. It uses a bunch of things, right? The figures that we're showing here is the best of everything, right? So we picked the best. I mean, it's easy to beat on slow systems, right? So it's easy to say you're 10x faster than naive implementations or semi-naive implementations. We're comparing
and like and this isn't just the Matmo level. This is like we compare against TRTLM. We don't compare against PyTorch Eager or something, right? And
exactly.
So it's about picking the speed of light that we know of.
Right. So we're not benchmarking here, right? This is like what the output was, and this is like, you should look at our benchmarking package.
This is not picking like, it's three columns wide, and somehow we got a cute trick that they haven't. This is like Llama 3.
Run the thing 3 times and divide by 2.
We expect these are the best, the most optimized things we can compare against, which is how we make sure that how I, as a point here boss, make sure that our team is actually doing good work, because that way we can compare and measure against state of the art that the industry is really driving towards.
Yeah, again, this is, Mojo is the foundation that our inference platform uses, right? So what folks compare us against is the best thing out there, right? Like either closed source or open source, right? And this is real money. The spend on AI is so massive that a flop or 10 flops equates to millions of dollars, right? So we care about those. Like, you have no idea how much effort went into like saying, okay, well, we're using int8 here instead of int32, or because it saves us a register, and things like that, right? If you think DeepSeek was doing wild stuff, we need to explain this to the world, but like it's like trivial for our case, and we're not bragging, right? I don't like to brag. But.
Yeah. Okay. Well, so let me paraphrase, and let's try to. So just Mark, if it's okay with you, I'll try to like constrain some of the questions. There's a whole bunch of questions about compiler stuff. We don't want this to be an 8-hour long talk, so we're not going to talk deeply about the compiler stuff. Please go read my blog post, Democratizing AI Compute. You can learn about all those other systems out there. We've given a ton of talks at the LLVM dev meeting. If you want to learn about like how we use MLAR and the crazy ass things we do to LLVM, et cetera, et cetera, et cetera. Like, so go there. We've given those talks before. But let me paraphrase what Abdul's saying. Like, we're doing this on hard mode. Like, this is not taking the quick and easy path. This is taking the hard path to try to get to a better result. Again, coming back to the point at the top, we think AI is worth it. We think heterogeneous compute is worth it. We want to unlock the silicon. Like, we're trying to do something that's quite meaningful, and it's really dang expensive. But again, and we've been working on this for years. That's why we're so excited to be able to say, you can download it now and go, and don't take our word for it. Just like be skeptical, but trust us enough to actually try it, right? That's the mode that we're in, and this is why I made Mark wait for a year before we were able to give the talk. So, anyways, want to keep going if that's okay, Mark? Or
let's do it. Yeah. No. Like, I think you should keep going, and we'll batch questions in the end.
Cool. Okay, sounds great. So we always get asked about other systems, and so I don't want to do a takedown of all the things. But again, remember, this is like designed for heterogeneous compute. So today we're being focused on what you could download and run today. And so there may be cool things over time. I'm very, very much a hardware nerd, but right now, again, grounded, you can run this on x86-64 systems. You can run on ARM64. You can run on any NVIDIA thing. We haven't done any Volta work, but go nuts. Like it should work. Theoretically, it should work, right? We've done some work on Ampere, Hopper, Blackwell. We've done work on AMD, the 300 series, right? And so we've put a majority of our work in the space, but being open source, this is where we'd love to work with other people and push it forward. Now, people always ask us about these things, right? And so how do you compare against Cutlass, which is part of CUDA? How do we compare against Triton and OpenCL? Like what we're trying to convince you, which is a high bar, is that we're the first system to actually deliver the full performance of the silicon. You could say our usability could be better. We're constantly improving things, and so I think that is to be true. But we actually provide way more portability than any of these on this map. And so that's actually, I should be careful about that. OpenCL has some crazy FPGA targets. So maybe not OpenCL, maybe we're not more portable than OpenCL, but this is a new creation, and this is very hard to do this. Now, I always get asked about one specific category that lots of people use, which is Python DSLs, right? And I think Mark was asking about this directly, but Python DSLs are what a lot of people are used to. DSLs are not like Mojo. So Mojo and DSLs are in the Python family. That is true. But the whole point of building a DSL, and by the way, I have a whole blog post about this. Please read part 7 for a whole explanation if you're not familiar with the technology and what a Python DSL is and stuff like this. But they're meant to be easy to implement, which is why there's so many of them. There's a ton. But it's really about prototyping. It's not about peak performance. And so you give up control to a compiler of some sort. There's different compilers out there, but you give up control to get more productivity. And productivity is really important, maybe if you're training or you're a researcher, or you're experimenting. But our focus has been on Gen AI inference and speed of light and TCO and things like this. And so this is a big difference. And so if you look at the advantages of Mojo, performance is number one. If you care about performance, if you care about inference, if you care about that, then Mojo is better than any Python DSL that I'm aware of out there. Also, like we've talked about extensively, you don't have to hack the compiler. And so if a new piece of hardware comes out, you don't need a new tiling strategy or algorithm or whatever. Just go write some code. Go write a for loop and go implement your own abstractions. And you don't have to like go change the compiler to be able to play with that, which is also a huge boon for research, by the way. Generality. So again, there's a lot of DSLs out there. They have different trade-offs, but many of them are limited to specific domains. And so Mojo, you can go write a ray tracer. You can go write arbitrary code. Not everything is a matmul and not everything's attention, even though, yes, those are extremely important, of course. If you want hardware, we've talked about this. Mojo's great for saying, like, I want this crazy ass thing that DeepSeek just reverse engineered yesterday or something, right? And so you get full power of the hardware. And that's something that when there's a compiler in the way that's trying to provide some weird abstraction for you that is helpful, it also is a downside because it's taking away control and power. And Mojo has, as we've talked about, the opposite philosophy. Metaprogramming. Well, so again, there's lots of DSLs out there. I haven't seen one that allows you to write portable abstractions. Often they're just about giving you tools so you can unlock one piece of hardware. And like if you go from A100 to H100 to B100, you keep having to rewrite your code. And so it's cool that it is easier to rewrite your code. But we believe that with the right abstractions, we can get more portability into this world and that can help people be more productive. Now, let me say the flip side of this also, there is no magic. It's not like you can have magic portability and things like this. And so we look for pragmatism, and it's better, and metaprogramming helps you do that. But still, there's always going to be cases where you do need to write hardware-specific algorithms. Tools. Abdul was just talking about this. Like, we think it's really important that you have a profiler that works. If you're doing performance, you want to be able to know how your code affects performance. And a profiler that maps back to your source code and without requiring you to stare at compiler IR to get your job done is really nice. And finally, I don't know if this is true, but I think it's entirely possible we have the biggest open source kernel library for GPUs anywhere. So if you want to check it out, that's pretty cool. And so that's production quality implementations of all your favorite friends, at least the ones that are used in GenAI. And we hope this gets better now that we've open sourced this literally yesterday. And so please check it out, and we'd love to work with you on this. So Mojo has some downsides. So the major downside that I know of is that it's still new, right? And so there's a lot of things out in the world that are 2 or 3 years old. CUDA itself is like 19 years old, quite mature. And so if rock solid stability is the thing that's important to you, then please keep using CUDA C++. If you want any of the benefits that we're talking about, then that's cool. The Python DSLs, they're also changing. And so maturity and stability is dependent on which one you look at. I'd also say that Mojo's like literally just coming onto the scene. So we were excited to do this talk with Mark's invitation because again, we're doing a bunch of open source and it's real and you can use it now and all the things we've talked about. But this is the beginning. And so if you want to be part of our community, we'd love to work with you. We think that, we've done some interesting things, but we don't have all the smart people. We can't tackle all the problems. And so we'd love to help build this future of heterogeneous compute because we think that the stakes here are quite big for the entire industry. So what we wanted and what we think that we're doing is we're building a unified GenAI native software platform from first principles. And so this is not easy because it's important and it's worth it. So let me wrap things up and start talking about like some of the other things that people always ask us about. Does anybody use it? Well, we're very excited that people are starting to use it. For example, Evan Owen at Quirky AI has been kind enough to say that Modular is massively simplifying GPU programming. They take what you're familiar with CUDA and C++, but make it type safe, Pythonic. They make it great to experiment and prototype kernels, make it fast while beating and meeting performance expectations. And so if you're a startup and you like moving fast, then you could be very interested in this stuff. All the stuff we're talking today is really meant for GPU programmers. We have other stuff that is cool if you're building models or if you're a platform engineer and things like this. But we think that GPU programmers are like a uniquely important and very special category of programmer because they're the ones that provide the power of the silicon. And so this is why we care so much about this. Like we talked about before, we've open sourced this gigantic pile of kernels. Like this is actually huge for us. This is the why now of giving this talk. Check it out. Again, I think that many people kind of assume snake oil or assume that there's like a catch. Like literally, we provide lots of links in the talk. Please go check it out. And you too can go see how SIMD works. And you too can go see how int works or unsafe pointer or all this kind of stuff. And so just go look at the code. And so this is the power of putting it in the library instead of hacking it into an opaque compiler. There's tons of kernels out there. And so like all reduce, lots and lots and lots and lots of code. Not only did we give the code, but we provide the full Git history. So I'll share with you that I'm a person that cares a lot about open source, and there's right and wrong ways to do open source. I've seen a lot of projects at many of the companies I've worked at that don't understand communities, and they don't understand that being open at the what that means. And so we're very committed to doing this the right way, and that's why we included full Git history going back to years of developing all this tech. Now, the flip side of that is that I've also seen the bad thing that happens when you're too open too early. So MLIR is one great example of that, where suddenly you get all the people that are in your business, you're trying to get it to work. And so what we decided to do was say fairly close until we got to work. We were happy with it, we're ready to scale it. And then just now we're opening this all up so that everybody can play with it and use it and go. And so please take a look. You can see all the mistakes we made, and like you can see all the different things that we traded off, and you can see both the output of what works, but you can also see the mistakes we made along the way. Oh, by the way, we have pip coming. So this is another big deal. You can technically do this today from our nightlies. This makes it super easy to download our stuff. By the way, our packages are really small. They're not as small as they should be, but they're like roughly 1 gigabyte for a full multi-architecture solution that runs on NVIDIA and AMD. Single image, super cool. pip is really important. We think this is a great way for developers to work. We think that this really enables us to work with the community, and hopefully, folks on the PyTorch team will find it really interesting, and we'd love to work together on making it super easy to extend PyTorch with Mojo, just like you can extend PyTorch with Triton and other DSLs. We haven't talked at all about Max, really. We've just kind of glanced off of it, but Max is a whole AI inference framework designed for predictability and control and performance, end-to-end, high-performance LLM serving, KV cache optimizations, continuous batching, and speculative decoding, like all that kind of stuff, that category of tech. We haven't talked about that at all. If you're interested, it's really cool. There's a whole like 500 of your favorite LLMs are out there, and there's more all the time. You can see a lot of them on builds.modular.com, and so you can go there. The models should be all open source too, I think. Abdul, do you know? Is that done?
Yes, yeah. So the models are open source, the server is open source.
Yep, and so you can go check all this stuff out. It's super cool. All this is coming together fast. For those that don't want to write all the GPU kernels and get the Tensor Core to work, there's even nice high-level examples, so you can see how to build a RAG example and things like this, and so that's pretty cool. We want to make AI accessible to everybody, not just the trillion-dollar companies out there, and so as part of that, we're trying to make this entire ecosystem, this entire stack, super easy to use, super consistent, super pleasurable to work with and iterate and expand. And so part of that is actually teaching people how to use it. And so that's one of the reasons we're excited to be here now and to be able to talk about this. Some people are like, what is the catch? Like, what can I do with this? Are you gonna like take all my GPUs away from me? Well, we're very excited that we actually want you to use this and we want it to be free. And so we have a what we call the Modular Community License. You can go to the webpage and read about it. You can use Max and Mojo and Max and stuff for free, unlimited use for non-production, non-commercial, researchy type things. Go crazy. You can also use it for free for production and commercial uses. The primary restriction is that we want you to be able to tell us about it. If you love what we're doing, you're serving production, we'd love to be able to use that as validation for what we do. For example, we'd like your logo on our webpage and stuff like this. We're still talking about how best to handle non-NVIDIA, non-CPU accelerators. And so right now we have some limitations around that, but we've been progressively opening and relaxing things over time. And so, yes, you can run Mojo kernels on 100,000 GPU training cluster if you'd like to do that. Go crazy. That's totally fine. That's really, really quite important. Yes, you can export PTX and don't use Max. That's also fine, right? We are modular. We want you to use bits and pieces, and that's totally fine. Now, if you're a production enterprise and you have a platform engineering team and you're managing distributed Kubernetes stuff, then awesome. We would love to help you with that too. But for this audience, like seriously, go write kernels. Next slide. Hardware, right? So like we talked about before, we've put a majority of our work on Ampere and Hopper type of devices, and so they're relatively mature. There are some minor features that are missing that are coming in all the time. Blackwell and AMD they work right now. You can go run them. We're still working on performance, and so out of the box, end-to-end LLM performance isn't fully there in all the ways, but we'd love to work with you on that. Modular is very focused on this Gen AI LLM space, and so we speak KV cache and radix attention and all this kind of stuff. We haven't put any effort into traditional AI. We haven't put any effort into like HPC applications or bioinformatics or all these different things. We want you all to do that. It would be really awesome. Like we don't have expertise in this. We're useful for the things that we know. We want the technology to go far and wide. Another thing we'd love help on is CPUs. And so if you speak AMX, which is basically a CPU Tensor Core, or SME, you're a Mac user and you're excited about the latest Apple Silicon, please like actually help us. We'd love to extend all this stuff. And if you can do that, then it makes everything better for the entire ecosystem. There's a million different things that are going on here. This is why we're open sourcing the kernels and open sourcing all this technology. And so we'd love to work with you together on this. So wrapping it up, come build with us. So we have a community that's just really opening up. You can download Max and Mojo. You can deploy models. It's free, like we talked about. Go export PTX and put it in your legacy system. Legacy, I mean, the system you've built with love and care. Sorry, I should not say legacy. Like the thing that you're already using, right? If you're interested in this stuff, and if we've blown your mind and you're like, I want to know more, but please help, please come visit us. We have a hackathon in the Bay Area in Hillsborough, California, near San Francisco. Mark will be visiting and we'll be talking, and we have an all-day hackathon type of thing. We have rewards, we have challenges. You could win a Blackwell RTX 5090, lots of cool stuff. It'll be a ton of fun. And so if you're interested, please check us out at modular/hackathon and come visit. Oh yeah, by the way, we're an amazing team. We're hiring and looking for amazing people. And so if you care about writing GPU code, and if you care about GenAI performance or LLM serving or things like this, please check us out. We have a careers page, and that would be cool. And so this wraps up the talk. I'm sorry we didn't get to talk about all the cool things, but hopefully this was interesting as a slice of what we're working on.
Hello, Abdul and Chris. So just for people to know a context behind some of this, Chris and Abdul met us during GTC, and we are like, okay, we want to do this, and we want to enable Mojo talk in the GPU mode. Chris was super excited and like, okay, I want to do it. I want to do it. I want to do it.
I get excited sometimes. this happens to me.
Yeah, and we were like, okay, it should happen immediately as fast as possible. And thank you everybody for joining in, and thanks Abdul and Chris for an amazing talk. I do have a couple of questions. So right now, there is a whole variations of the different capabilities to do, like multi-GPU enablement and doing the communication across them with different mechanisms of doing the communications too. Like there is a whole lot of like complexity that is associated with it.
All reduces and things like this.
Yeah, exactly. So any thoughts on how this can be enabled in Mojo, where it is, and what's the plans on that? I mean, you spoke a lot about doing compute orchestration or compute jobs and all, but less on the other side of things. So I want to hear your thoughts on those.
Abdul, please tell us about AutoFusion with all reduces.
Yeah. So I mean, go to again, go to GPU/com/all-reduce. You'll see an all-reduce primitive, also all gather. We plan on adding all to all and so forth. By the way, it's portable, works on AMD, NVIDIA. There's certain instructions on Blackwell and Hopper that we need to actually do that. Implement the all reduce. The primitives are there for folks. Actually, that's a great hackathon project, or folks are interested in contribution using multi-mem and so forth. But also, like, it's again going back, it's the composition. All reduce is not the only thing. It's all reduce followed by, or mathmal followed by an all reduce, or an all reduce followed by activation and so forth. We are actually very capable of doing that. Again, nothing is and by the way, all of this is written in Mojo. We're not using Nickel or anything like that. But if folks want to use like MVSHMEM or Nixel or other things, again, there's full compatibility. You can go to the FFI package. You can call any C++ or C function if you want, right? So there's nothing stopping you from using Nixel or something else, or Nickel or Rickle or MSickle or whatever the call you want exactly. But today, our all reduce is actually faster than Nickel's all reduce, right? For within a node, right? And we also do fusion, so that's kind of novel for this thing, and we use PDL as well, so that we can overlap the mathmal with the all reduce as well.
Yeah, so let me just frame this up a little bit. I just switched my earpods out. Can you still hear me?
Yes.
Yeah. Okay. Cool. So we don't like dependencies, and so this is when you hear Abdul say we don't use Nickel, we don't use CUDA, we don't use any of this kind of stuff. It's because dependencies have lots of bad things that come with them, and so we typically re-implement the stuff that we really care about that's important to us. But you can call into all these libraries in this ecosystem as well, and so. But Vikram, to your question, right? This is like the mind-blowing thing, is that when you get out of affine math compilers using polyhedral blah 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 blah,
Yeah.
Well, suddenly communication isn't special, right?
That is fair. Yeah, as long as we can map it
talk to
very well.
arbitrary things that you might do with your accelerator, and this is why, we can autofuse, because we're not autofusing with affine math and linog blah 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 blah. It's a fully general algorithm, and so that's like, again, a very different thing in the ecosystem, which makes it all just way simpler, right? It's not that, to be fair, like you can achieve a fused all reduce or something with CUDA, but it just means that you have to like write the permutations, right? And so this is where a language integrated with the graph compiler, as far as I know, has never been done like this. So
That is true. So I think that is one of the unique way of you guys are handling this scenario. You spoke about releasing some of the piece of code in public. What's your plan on your roadmap to release the compiler, the Mojo compiler? Is it there in the radar, or how are you thinking about that? So
yeah. So this is something that I annoy people with. So this is a frequently asked question. Let me before I answer the question, I'll tell you my backstory on this, right? So
sure.
I'm known for things like LLVM and Clang and the Swift programming language.
You are an open source person, so that's the reason I'm asking.
I like open source. The thing that most people don't remember is that none of these were open source initially. And so LLVM was built in secret for 3 years. Clang was like literally secret even for most of Apple for 4 years, and then it got open source 2 years later. Clang was open source it was proprietary one building, and then we released it from Apple, et cetera, right? There's a reason for that. And one of the things I learned and was reaffirmed was with MLAR. And the problem with MLAR, and I wrote about this in the blog post series, is that I was trying to build a compiler construction toolkit, and then it wasn't done, but everybody's like, oh my God, there's a thing, I want to use it, I want to go do stuff. And they built all of this legacy code, much of which are now the MLAR dialects, by the way, while MLAR was still just being created. And so what I really believe is you need to get a new novel creation to a very consistent point, and it's actually baked before you invite the community in, because yeah, it can be fun to have like lots of opinions on syntax or something, but it doesn't make me get to success faster. And so what we decided to do with Mojo is say, okay, well, we'll open up the parts that we want contributions, we'll open up these pieces over time, and then you know, I want to get some of the basic type system stuff really nailed down, because unless it's helping us get to victory faster, like I'm not, you know, it's self-defeating. And so we've committed that we're open sourcing Mojo by the latest end of next year. So maybe sooner than that, but we've made that commitment to the world.
Thank you. Thanks for giving the clarity. So.
Okay, so I think now might be like a good
thing I would say. By the way, just to give you a snippet and a snapshot of how weird Modular is, right? So we have a monorepo at Modular. We have more Mojo code in our monorepo than C++ code. So this is not like an abstract thing that we do for fun because we're messing around with it. This is like, we're building this thing because we use it. And so this is really, really important. And so this is not like an abstract academic project. This is like really important that we get it right. And so we want everybody else to use it too. And so that's why we're opening up and everything else. But again, my incentive, again, as a guy who builds things that take years to bring to market and that then have large impact on the world, like the incentive is make sure it is right. And if it takes a little bit longer, and if people are shaking their fist at me for a while, that's okay. I can take it now.
All right. Like, I think on that note, like, I think Chris, like, thank you so much for joining.
Yeah.
I figure sort of like the sort of recurring, I think maybe the main takeaway for people should be there's sort of a lot of like very fancy features we talked about today. Just like go try it out, share your benchmarks on the Discord server. Let us know how it goes. I'm going to be personally hacking all day on Mojo Saturday of next week just to see like what it's like for myself. I think like basically if a lot of the promise of like performance portability is true, then you know what we should do is have you guys be topping both like an NVIDIA and AMD leaderboard on our server. And I think like I'd love to work with you on that. Like basically,
yeah, I was about to tell that. So Mark, we should just have Mojo kernels executed on our kernel bot scenario, and then say, hey, yeah, this is amazing.
That's the ultimate flex. But